Hello everyone, welcome to lecture 6 of module 5, which is on 3D NAND flash memories. The disclaimers remain the same. So in the last lecture, we were discussing about the different configurations of 3D NAND flash. So we looked at, the vertical channel based NAND flash, which consists of cylindrical channel. And we also looked at the vertical gate based 3D NAND flash, which consists of rectangular kind of channel. So we looked at vertical channel as well as the vertical gate kind of configuration. So here we will just be, doing a benchmark of the performance of these different flavors of 3D NAND flash against the 2D floating gate flash or 2D charge trap based flash. So if you look at the first point, which tells you about the gate structure, while it is planar, that is, it's only on one side. In the case of your 2D NAND flash, it's a gate all around configuration for your vertical channel based 2D NAND flash, and it's a dual gate structure or a twin gate structure for your vertical gate. So this way, which one is better? So gate all around structure gives you the best control over the channel region. So this way, your VC is kind of best. Okay, so now let us look at the next point, which says about the unit cell size. So here it is not the effective cell size, which kind of considers your bit line contact, word line contact, and your select transistors, but here it's only talking about the cell size. So cell size wise, your 2D NAND flash and vertical gate NAND flash, 3D vertical gate NAND flash are occupying area of 4f squared. However, area occupied by this vertical channel is 6f squared. And why is it so? Because its dimensions are kind of determined by the thickness of ONO layer. Here I told that deposition is something which determines its kind of area, and this area. So let me write this as well. So here in your VC, in your 3D VC NAND, your dimension or your cell dimension is limited by ONO thickness plus core filler thickness of macaroni body plus what? Plus your polysilicon thickness. So that is why your effective dimension is kind of effective cell dimension, like your physical cell dimension is higher as compared to your vertical gate or your 2D NAND flash. However, let me write this as well. If you look at the effective cell size, which includes WL, BL contact, BS like BSL, SSL, source line selector, or SLS, whatever you call it. So SLS, if you consider the effective cell size, then since BSL, SLS, and WLBL contact, everything is included on this like vertical channel itself. So on that pillar itself, you have this SLS, you have this BSL. You don't have to, kind of and have another kind of transistors for that, right? So effective cell size of VC, so the effective cell size of VC is kind of greater than that of VG. Sorry, it's kind of less than that of VG. It's less than that of VG. Because for VG, what you had was, so let me write that as well. For VG, vertical gate or like horizontal channel vertical gate, which is this configuration, you had to use several SSLs, right? You had to use several SSLs in order to, select one particular layer amongst different layers, or select one particular string amongst different strings. And that is the reason why you have the effective overhead of VG as very high as compared to that of VC. So effective cell size of your vertical channel is less as compared to the vertical gate configuration. And then what is the barrier for physical scaling? As I already told here, that it's the deposition or the film thickness of ONO and core filler and polysilicon for your gate all around VC kind of structure. It's lithography for your 2D NAND flash, and it's lithography in one dimension for this vertical gate, and its thickness in the other dimension. So another point that, like another kind of important conclusion that we can make from here is that your VC is least sensitive to lithography. And since it's least sensitive to lithography, scaling is not a big issue for it, right? Okay, and now let us look at the cell swing. So swing is kind of highest for 2D NAND. The sub-threshold slope kind of improves for gate-all-around and for your vertical gate. However, if you look at the cell current, on current of the cell, it's 2.3 times higher for gate-all-around and it's only 1.2 times higher for your vertical gate. And why is it so? Because since the gate is kind of wrapped around the channel region, your effective inversion layer dimension or inversion layer volume is higher, because you have inversion from all sides, while in the other two you have inversion from only one side or only from two sides. So then they talk about coupling. So here in 2D you have strong word line and bit line coupling, as we already discussed, and that is the reason for moving towards your 3D kind of structure. So here it's almost zero in the vertical direction. However, there is a coupling. I would talk about that, and why is it low or moderate in the case of vertical channel or vertical gate? The reason being that the SI3 and 4 thickness is pretty small, and because of that, the coupling between neighbor cell is low through that. But there are some other ways in which the charges get lost, and we'll be discussing them in the next slide. Regarding programming arrays, the same kind of functionality is being used, all three of them. Then regarding program disturb, it's channel coupling in the case of 2D, whereas it's neighboring, I would say it's kind of neighboring nitride layer disturbance that I will discuss in the next slide. So don't worry about it. And the cell overhead, you can see that it's almost zero for your vertical channel, but it's kind of 35 to 70% just because you have several SSLs in the case of your vertical gate. And the lithography, you can see that it's very weak over here, while it is kind of moderate for your vertical gate, and it's kind of very strong for your 2D NAND flash cell. Okay, so now how exactly will you find the cell size of your 3D NAND flash cell? So in 3D NAND flash, especially the VC cell, what you have is you kind of etch holes or plugs, memory plugs, in a stack, right? So usually the process that they used for etching is DRI, and ideally you should get cylindrical cross section with uniform diameter. But what you end up getting is the kind of diameter at the bottom is very small. So let me draw that using the right pen. So the dimension at the bottom is really small, and this dimension kind of corresponds to the minimum kind of thickness, and that thickness includes ONO plus filler plus polysilicon. While this is the minimum size, or I would say this is kind of the process dimensions of ONO plus filler plus poly, but since using any process you cannot etch perfect cylindrical holes, what happens is you end up having a tapered etching profile. So end up having a tapered profile. It kind of forms like a cone, and the diameter progressively increases as you go towards the top stacks. So at the bottom you have the least, at the bottom you have the least thickness of the hole, and the dia kind of increases as you increase number of layers, or as you increase the height of from where you have to etch the holes. So just because of this tapered holes, what you end up having is you have F process at the bottom, and you have some diameter which is very large as compared to F process, and the cell area is kind of considered as the area that is occupied by the topmost kind of the topmost, I would say, diameter, and that is not defined by the critical feature. That is not defined by your ONO thickness, minimum ONO thickness plus filler plus poly. That is defined by the taper angle which you obtain using etching. So let me write it. So this thing, I mean the cell area, it's not the minimum ONO thickness, minimum filler thickness, and minimum poly thickness which is determining it. What is determining it? So it's being determined by first number of layers. Why number of layers? Because that determines height. This dictates height. And The larger the height, so height increases or WL layer increases, the taper angle increases. Taper angle for etching, that increases. And this leads to what? This leads to higher F area, or effective area of the cell kind of increases. Your cell area is actually increasing, so let me call this C area. The cell also in the vertical channel kind of configuration, as you add more number of layers, what happens is, so let me write that as well. So let me write it here. So as WL increases, as you add more number of layers, what happens is you're kind of putting more number of cell in series with the desired cell. And even though you are applying a VPass to all those cells which are unselected, they'll still contribute to some amount of series resistance. So as you increase the number of WL layers, your series resistance increases, and because of that your string current reduces. So if your string current is pretty low, then it becomes very difficult for the sense amplifier to kind of identify between two different states, right? So that is the reason why you cannot incessantly kind of increase the number of WL layers in any 3D NAND flash. On the other hand, if you look at this vertical gate structure, here if you kind of stack even more number of layers of horizontal channels, then it's not going to affect your string current. So that way vertical channel and vertical gate are also somewhat different. Okay, now with this kind of information, let me also talk about the retention issue of 3D NAND flash. And let me tell you that it is kind of worse as compared to your 2D charge trap or 2D floating gate cells. So let me just talk about the different mechanisms which may lead to loss of these charges. So it is shown in this figure on your right. If you see this figure on the right, now let us try to identify these physical mechanisms which are responsible for charge loss from the nitride layer, which is stored in the nitride layer. So let us talk about one first. So what is one? So one is FN. So FN tunneling of electrons from the conduction band of the trap into the conduction band of the tunnel oxide or blocking oxide, and from there it can go into either side. So then apart from that, let us talk about 5, because these are easily identifiable. So what is 5? So 5 is nothing but trap to band tunneling, right? Now let us talk about 2 and 3. So what do you think about 2 and 3? What are those mechanisms? So 2 and 3 are kind of trap to conduction band movement of electrons. What can be the processes? The processes can be thermal injection, thermal excitation of the electron. It can be SRH, Shockley-Doll recombination, and it can also be Poole-Frenkel mechanism. And amongst these three, thermal emission and Poole-Frenkel, they are very sensitive to temperature, right? You increase the temperature, your Poole-Frenkel hopping increases, and your thermal excitation also increases. Also, compared from 2D, also there is this new component 4, which is kind of because of drift and diffusion of electrons within the nitride layer, within Si3N4 layer. So what can happen is, since this nitride trap layer is continuous, these electrons may migrate from the bottom of gate 2 towards the bottom of gate 3 or gate 1, depending upon the fields, depending upon the temperature, depending upon the gradient. So this kind of drift and diffusion of electrons within the nitride layer is called lateral migration. This is called lateral migration. And this is really one of the major concerns of this 3D NAND flash memory. So how they kind of characterize the reliability of 3D NAND flash? So what they do is, they kind of first do the distribution of initial erase distribution and the initial program distribution. Then what they do is they bake it. So once they bake the wafer, they kind of give enough energy to the electrons so that there can be this two and three mechanisms which are possible, like thermal and cool frontal mechanisms get activated. And also, if you're giving a large number of energy to the electrons, even the drift and diffusion mechanism is kind of accelerated, right? So because of this, what happens is there is a migration of electrons from one kind of charge trap cell to the other charge trap cell. And when you kind of measure this threshold voltage after baking, what you'll see is that the distribution has kind of changed. You see that the distribution has changed, and there is a kind of overlap between the program and the erase kind of distribution. So here the reliability is lost. So I would say that here, just because of this charge migration or retention loss, what happens is your reliability suffers. And here we have shown the results for two different kind of patterns, of programmed cells. So here this is a solid programming, which means that all these different cells are programmed to the same value. So let's say you have electrons, or you have electrons in the charge trap layer at all these beneath all these gates, or beneath all these cells. However, in the second case, it's a checkerboard pattern. So the checkerboard pattern simply means that you have electrons on the first, but you don't have any electron in the adjacent or the neighboring kind of cell. Then again, you have some electrons on the neighboring cell, but you don't have any electron on the other neighboring cell. So this checkerboard pattern, if you look at that, if you look at the checkerboard pattern, so the checkerboard pattern will also generate some kind of electric field. So the checkerboard pattern also generates an inherent electric field, and because of that E field, what happens is your lateral migration is accelerated. So if you look at the distribution, so this was the initial erase and initial program distribution, but after this temperature baking in a checkerboard pattern, what you see is the kind of overlap. The erase and program distribution kind of overlap, and the reliability goes to kind of zero. So it's not at all reliable now. You cannot even work with this kind of checkerboard pattern and this kind of cell. So this way, this lateral migration is very important concern for flash cells, especially 3D NAND flash cells. So how we can reduce this lateral migration? So lateral migration is just because you have these word lines very close to each other, and these electrons can migrate from one word line, beneath one word line, to beneath other word line. So one way to kind of reduce this amount of lateral migration is increase the word line spacing. Since it's a vertical structure, it's like this. Even if you increase the word line spacing, it won't affect the area, right? Because the area is still what is consumed by this bottom point. However, if you increase the word line spacing, if you increase this distance, what we told is, here we do not have source and drain regions. You generate these virtual, because of these fringing fields, you kind of invert these regions and generate virtual source and drain regions. So let me write that. So the fringing fields generate these virtual source and drain regions. So if these cells are placed far apart, then only in some region which is very close to this, these inversion regions or these virtual source drain regions would be generated. And in the middle, you would expose some region which is undoped, and because of that, what would happen? Because of that undoped region, so let me write it. Because of that undoped region, your series resistance will be high, and because of this high series resistance, again your string current reduces, and it is detrimental for your sense amplifier. So even this is not a very feasible solution, increasing word length spacing in order to mitigate, this lateral migration. Because of your curvature effect, field is high near tunnel oxide, right? So loss of charge in nitride due to process 1 and 5 near TO is large as compared to 1 and 5 near blocking oxide. That is one point which I wanted to mention over here. Also, although Samsung took like 2 years to come up with this TCAT, in this TCAT, it already mitigated the issue of lateral migration. How? So if you look at the big structure, since it's vertical, so your SI layer is kind of continuous, like this. So the electric field direction is like this, and electrons can easily migrate. So let me write it. So in your BICS, your nitride layer is continuous and vertical, and fields, electric fields, due to checkboard pattern or any other pattern, these fields may facilitate your lateral migration. On the same, like on the other hand, in this TCAT, although this nitride is continuous, but it follows a different pattern, right? So the nitride here is zigzag. So nitride here is zigzag. Let me just write. So nitride layer in TCAT is zigzag, and just because it's zigzag, even though the field is in vertical direction, because of this zigzag shape, not all electrons are forced to move beneath the neighboring cell, right? Because the field is in this direction, and in order to move towards this, they'll have to traverse a path like this, a zigzag path, and there is no field assisting its motion along this zigzag path. The electric field is in the vertical direction, while the path that it has to take in order to go from one control gate, beneath one control gate to beneath another control gate, is a zigzag path. So because of this, TCAT is superior to BICS. So you see, Samsung took 2 years, but it came up with something which is really great. So to mitigate this retention and reliability issue of 3D vertical channel NAND flash, SK Hynix in 2010 came up with this idea of 3D floating gate NAND flash. So let me write it somewhere. So SK Hynix, which is another leader in the memory, it came up with this 3D floating gate NAND flash in 2010. So several structures were proposed. One of the first structures to be proposed was this ESCG. So let me write its full form. So its full form is extended sidewall gate, sidewall control gate. Sorry, that makes it ESCG. So what it had was, it had these this kind of extended sidewall gate, and this was the floating gate, which was kind of gate all around structure. And with the help of this kind of extended sidewall gate, it was kind of influencing floating gate, and at the same time, it was kind of inducing these virtual source and drain regions, which is represented by this electrical SD layer. So ideally, you only require, so let me write it somewhere. So ideally, we only require coupling between floating gate and control gate. But here, the extended side gate also provided virtual source and drain regions, or electrical source and drain regions, which was kind of beneficial for this kind of 3D structure. But again, the disadvantage was that if you have another kind of floating gate stacked on it, that if you have another kind of floating gate which kind of covers it, then there would be a huge coupling between this ESCG and the neighboring kind of floating gate, which would be here. So neighboring coupling distance, neighboring disturbance was not yet overcome with the help of this kind of structure. Then the second kind of, I would say, innovation that also came up from Hynix itself, and that was kind of called this dual control gate. That was called dual control gate kind of structure with surrounding floating gate. So there they used two control gates. This was one control gate and this was another control gate, and the floating gate was kind of inside to kind of have this operation. And however, even here, however, in both these configurations, neighbor cell disturbance effect or what should I say, the floating gate to CG coupling of neighboring cell is dominant. To mitigate this kind of coupling, what they came up with is shown on the right. This SSG unit cell. So here you have separate control gate. So here what you have is you have control gate and floating gate. Both of them are isolated and shielded by these SCG. So you have two SCGs, one at the bottom, one at the top, and these two are kind of shielding your control gate and floating gate from the control gate and floating gate, from the control gate and floating gate of cells at top as well as cells at bottom, right? So here this SSCG or this SCG gates kind of providing a shielding effect to this control gate and floating gate. And what is the use of this SCG? So as I told, as was the case here also this SCG is used to produce virtual source and drain regions so that the series resistance is reduced. Okay. So let me summarize our entire discussion and discuss about what are the advantages and disadvantages of this 3D floating gate test cells. So let me first talk about the advantages. So definitely we get an advantage in terms of lower charge spread of nitride layer because there is no lateral migration component. And if there is a lower charge spread, what it leads to is you have kind of a better multi-level capability, right? And also less complex ECC also can work here. So ECC need not be very complex. That is another thing that we get out of it. Another advantage is better retention. I mean, that is the reason why we went for this 3D floating gate NAND flash cells. The third advantage is you don't need, so let me write it. You can perform bulk erase. So bulk erase is possible. We don't need to go for, no need for GIDL, as was the case for BICS. Now let us talk about the disadvantages. They remain the same. I mean, major part of it is attributed again to the coupling issues. So disadvantage first, cell size is large, right? Cell size is large. Why so? Because you have to incorporate these floating gates. I mean, you have to incorporate these floating gates, which are large. So just because you have to incorporate large floating gates, your effective cell area is also large. The second issue, and that I find is the most important issue, is the coupling effect. Although you can introduce several structures like this kind of shielding gate structure in order to avoid interaction between the floating gates of neighboring cells, or kind of shield them using a control gate like what has been done here, or the SCGs over here. So you can kind of use these techniques to avoid this indirect component of tunneling, indirect coupling component. So there are two components of this coupling. One is your indirect coupling. So that is between FG and FG through shielding. Shielding CG or shielding whatever it is. So you can kind of reduce that by using these kind of shielding gates. But there is something which is called direct coupling through this string itself. So that kind of coupling, which is through the string, that is your floating gate kind of couples through the string to this floating gate, or it kind of couples through the string to this floating gate. This kind of coupling is really difficult to avoid. So you can't work around this direct coupling issue. Through the string. Okay. So these are kind of the problems with 3D floating gate NAND flash. And now I can proudly say that you guys, if you kind of go through these lectures properly, you guys know much more about these kind of 3D NAND flash memories.